Okay, so the topic for this week is flow through porous materials. And what I want to do in lecture is really highlighted here. We'll start off with some applications and examples and just show you why we would be interested in understanding flow through porous media. And then we need to come up with a way to analyze it. So we'll start with a conceptual model about that, and then I want to go and show you basically the basis for the setup that COMSOL is using that we will then also use for solving flow through porous materials. And so we'll need these governing equations and parameters and initial conditions and so on. And this will be a similar kind of outline for all of the each week, really, all the lectures. Okay. So applications. One of the things that I've tried to do with the class is to take kind of a broad look. And so there are many applications from a variety of fields, from engineering, from hydrogeology, and from a variety of other things. So this is a kind of a starting point. This is really an example from engineering where we've constructed a device where we want to filter some things out of water. So sand filter or perhaps other types of material. Here's a sintered nickel filter, and basically, you zoom in here and you see this structure of the material with some solids and pores and the fluids flowing through the pores. And here's kind of a more elaborate version of this that is used for water treatment. And as it turns out, sand filters play an important role in how we analyze flow through porous media, because it was an experiment done by Darcy back in the middle 1800s on sand filters, or basically an experiment that he did trying to understand how sand filters work, that led to Darcy's law, which is an important foundation for understanding flow through porous medium. Basically back in those days, the water supply in towns would come in, and they had pipes, but they didn't really have pipes that could go to each house. So you didn't have running water in your house. You had running water to the town, and then you had a central point where you had to go and get it, and usually you would go just manually. So the towns that this was done in France, so the towns in Europe at the time would have these fountains in the town square, and here's an example of one, and this is kind of ornamental with these spouts of water coming out like that, but they served a practical purpose because this is where people would go to get their water. Darcy was involved with designing these things, and they understood about, this was right in the beginning of understanding about waterborne pathogens, and they understood that if you filtered the water through sand, you could improve the water quality. And so Darcy wanted to understand about the head loss during flow through sand so that they could put the water through a filter but still have enough hydraulic head to make these fountains work. So he set up a test that's shown here. It's it's a column filled with sand, and there's water flowing up here and out like that. And he was measuring the head with these manometers, and he showed that the flow through the sand filter was linearly related to the head gradient through the sand filter. So expressed in flux, he had the volumetric flux was equal to a constant times the head gradient. And so that became known as Darcy's Law, and we'll get back to that later, but it had this very important origin in understanding how sand filters work. So we can take a look around us, and there are many applications or many examples of flow through porous media, and plants are a really good one. Plants have many small pores with fluid flowing through it, and that fluid flow is an important part of how the plants work. Here's a photomicrograph of a piece of wood, and you can see these pores that look like a bundle of tubes. And this is a piece of woods out of a tree, and what's happening is that, at least in a simple sense, there's water down here in the ground. It goes into the roots and goes up through pores like this up to the leaves, and it gets evaporated out. So flow through porous media is important to how plants work. It turns out it's a little bit more complicated than that sketch, because the flow through plants can go both ways. And here's a picture of that tree. What's happening is that on this internal part right in here, that's where the flow is going up. And then some of the water is evaporated out of the leaves, but then there are also chemical reactions that occur in the leaves that create compounds that the plant needs, and that stuff moves back down through this outer layer. So this is just showing it schematically. The water is flowing up in the material called a xylem. Then there are reactions up here that take place, and we have fluid flow going back down the plant, down back into the roots. One of the compounds that's made up there is sugars. So where you have, this is, I guess, an example of a sugar beet. So, you've got an example there where you have sugars down in the ground, and the way that works is by this circulation process of flow upwards to the leaves. The sugars are made up in the leaves and then transported down into the root structure, into the sugar beet. Okay, so we can also take a look at other naturally occurring examples from living things. There are many examples of flow through porous media in you. Porous media are a good way to exchange compounds. So in internal organs, in lungs and kidneys, where you need to exchange, in case of lungs, oxygen between air and the blood, you have these small pores here in these lung tissues. Here's a zoomed in one. So there's this pore where the air is flowing, and there's blood in the walls here, and the very high volume to surface area ratio is how the exchange of oxygen really can take place. Similar thing in kidneys. Here's a photomicrograph of kidneys. You can see many small pores, and that's also used as a way to exchange compounds. Okay, so probably what a lot of us are interested in is porous media that's formed from rock or sediments, where the solid matrix is some kind of a mineral structure or perhaps some kind of organic material, and the pore spaces are shown here. And there are a variety of different flavors of this depending upon what the solid materials are. Here's a vesicular basalt. So these pores are small gas bubbles that are formed in a molten rock, and as the rock cools, the gas bubbles there are quenched in place, forming structures that, in that case, those pores may be connected or they may not. They may be fairly isolated pores. This is an example of porous material that's just this is a pretty idealized picture of some grains of sand, and so this would be an example where these pores are fairly well connected with each other and really pretty idealized pore structure. What you end up with is kind of a complicated geometry of these pores through which the fluid's flowing. So one of the things that's happened over the past 10 or 20 years is people have been using medical imaging techniques to take a look at what the pore structure actually looks like. So here are some pictures of some sandstones, and they have different amounts of porosity. Porosity is the ratio of the volume of the pores, which is what you're seeing here shaded, to the total volume. So this is 22%, and this one is a smaller percent. You can see the outlines right in here. For example, that's where a solid grain would be. Maybe one right in there. So this is a fairly well-rounded grains, and then this is the pore structure that you see. As you reduce the amount of porosity, you get obviously there's less porosity in here, less pore space, but also what you see is that the pores, like look at this guy right here. So there's a pore, it's fairly decent size, but it has that it necks down to a very small neck. So this pore is connected to this space, but there's a very narrow neck that it has to go through. In other cases, there are these blobs like that one there, or that one there, where the pores are isolated, at least according to this image. And so, you can see how that would happen, I think, with this vesicular basalt, but in other cases, you can also have the pores isolated. So the geometry of the pores will play a role in how the fluid flows through the material, and also how things are transported through the porous material. So here's some other examples. The imaging technology is pretty sophisticated. The oil industry has found that this is a valuable thing, so they have resources to put into developing some pretty fancy imaging capabilities here, where the different pores, the interconnectedness of the different pores are tagged like that, so you can get a pretty good idea of what they look like. Okay, so that's what these porous materials look like when we go in and look at them at the small scale, where we can see the structure of the porous material itself, see what these pores look like. They're fairly complicated geometry. And we'll be interested in understanding what happens at that scale, at the pore scale, where we have this complicated geometry, and where we have things that are in the fluid, in the pore space, moving around and interacting with the solids. And so we'll do that actually, I think next time or the time after that. But what I want to focus on for this class is looking at applications that really are at a bit of a larger scale. And if you're interested in something like this, where this is a cross-section just through a hillside and showing the groundwater flow. This is an example, of course, of porous media flow, but this is at a scale that's large enough so you really can't deal with this on a pore by pore basis, and so we need to be able to scale it up and analyze larger domains where we're not really considering individual pores. We also, shown over here, have a variety of different types of pores, porous material that we might be interested in under natural conditions. Here's our idealized picture of some nice, fairly well-rounded grains of sand with a pore space between them. This is some fractured rock where we've got a pore space with quite a different geometry. Perhaps this material here is sandstone, and if we look closely, we might see something that looks like this, but we can also see that this has much larger pores through it, and we would have to we'd have to be able to consider those pores as well. So flow of groundwater will be one important application, but there are a variety of other fluids flowing through porous media that we might also be interested in. Oil and gas reservoirs are a good example. And so we'll keep that on the list of things that might form important applications. Okay, so that's kind of a quick run through some of the things that we might want to do when we understand porous media, or some of the applications for it. Now, to analyze this process, we want to go and take a look at how we're going to do that. So here are the steps. We'll have a conceptual model and then get into some of the equations. And ultimately what we're going to want to be able to do is determine the distribution of pressure within the porous media and the distribution of flux. So flux is a vector, so we'll need to know what the magnitude and direction and how that is distributed through the region that we're interested in. Okay, so some of the general concepts that we'll use. One is that the properties that we'll be interested in are averaged over a representative volume. So for what we'll do today, we're not so much interested in what happens at the pore scale, but what happens at this what's called a continuum scale, where the properties of the pores are averaged out. And so that'll form an important basis. I want to show you, though, one of the consequences of that is just how we get the governing equations to work at this continuum scale. But that'll be an important concept. And then we'll have these the conservation concepts. So for flow through porous media, we'll have mass and momentum conserved. So those will be the starting points. So for the continuum, this representative elementary volume, and basically what we're doing is taking this thing here. This is one of these images, these pore scale images, and saying, well, that's interesting, and that's where the native processes are active, but it's really way too complicated for us to deal with, and so we're going to average out those properties, and instead of dealing with the left side, we deal with the right side, where everything is continuous within that block. The properties are continuous and uniform within that block, but they may vary, but within this kind of a scale, we can use the average properties of stuff on that side. So here's an example of kind of well, when I put this together, it was an animation. In the format that we're seeing here, it shows you all the animations at once. So let me just show you the way that this works. If this is these are pores and pore space, then our REV is basically a region over which we average. So if we take one of these small pink blocks, then if we have that one, and if we're interested in just the concept of porosity, the ratio of the volume of the pores to the total volume. In this case, the REV is the total volume that we're averaging over. So for an REV that's this size here, the pores are equal to the total volume. So the porosity would be 1 right here. But if we move that size block over to here, say, then the porosity would be 0 because it would all be solid. So the porosity would be there. And if we move it around, we could have that size right there, and it would be 50%. So for an REV that's this size, that's like smaller than the grains, as we move it around, we get that porosity varies from 0 to 1. So, I mean, it's interesting. But if we want to say that porosity is a property of the REV, then it doesn't really work It doesn't really work too well for us. And so as we make this block larger, we can see that at that scale, as we move it around, here the REV is getting bigger. Then we have, depending upon where we put it, we might have a porosity here if we're mostly in solids, and if we move it over a little bit and mostly in the pore space where we have it here. But then as we get this thing bigger, and we have something this size, and we're up here, then this shrinks down. And so the concept then is that we get an averaging region that is, I don't know, in this kind of sketch, if it's say 10 times bigger than the pores, then as we move it around, the volume of the pore space to the total volume isn't really going to change much. And so we're out here, and in that case, at that averaging volume, we have porosity providing a meaningful averaging, or a meaningful, being a meaningful property because it's describing the porous media in a way that's not really changing with space. Okay, so that's pretty good. So we would be working in here. This REV size where this works, for example, like this, maybe it's 10 or 100 times larger than the pore size, then we can average out all of the variations. One of the things that we have to keep in mind is that that's only going to work if we're in a sedimentary rock, for example, or really no matter where we are. As we move around, the porosity may stay constant until we move far enough away so that there's some other rock or some other material, in which case the porosity would differ. Okay, so this doesn't necessarily, so the porosity can change spatially. The other thing that can happen is as this REV gets bigger and bigger, we're incorporating other types of materials, and so the porosity that we get by averaging within the REV, if this plot is extended, then it may change just because of how the say different layers in a sedimentary rock would have different porosities. So this REV concept, on one hand, it's pretty easy to accept that, well, we're just going to take a volume and average and use those properties. But we see that there are problems with that if it's too small, and there are also some, the values will change also as the REV size gets larger. So there'll be kind of a sweet spot for the REV size where the property stays relatively constant, and that would be the size that we'll want to, what we're going to assume is applicable for these